All right, so in this section, we're going to be taking a look at a couple different ways by which we represent our chemical formulas. So we're going to be talking about something known as empirical formulas. But before we get to empirical formulas, we need to first of all understand what the molecular formula is. So when we talk about molecular formula in the first place, okay, what we are referring to here is, in the normal sense, the chemical formula for a compound, and this represents the actual number and type of atoms in a compound. Okay, and the key thing here, it's the actual number. So for example, we can have something like butane, which has the chemical molecular formula C4H10. Now, what the empirical formula is simply the smallest or the simplest whole number ratio. So the smallest whole number ratio of atoms in a compound. So for example, for butane, which we've seen has the molecular formula C4H10, we can simplify that by dividing each of those subscripts by a number that will give us the smallest whole number ratio. All right, so we can divide both of those subscripts by 2, and what we end up with is C2H5. And that's the smallest whole number ratio between the carbon and the hydrogen. So this here will be our empirical formula for butane. All right, so it's the smallest whole number ratio of the atoms in a compound, or the smallest integer ratio for the atoms in a compound. Here are some other examples. So for instance, acetylene, our first one here. If we divide both of these subscripts by 2, right, then we end up with the subscripts being 1. So we have 1 carbon to 1 H as our empirical formula. If we look down here at glucose, all right, if we divide our subscripts by 6, right, then we end up with 1 carbon, 2 H's, and 1 O, and that'll be our simplest formula, our empirical formula for that compound. Let's take a look at how we can calculate and determine the empirical formula for a substance. So in this example, it says, what is the empirical formula of the compound if experimental analysis shows that the sample of the compound contains 6.87 grams of iron and 13.1 grams of chlorine? So what we need to do, our first step here would be to determine or calculate the number of moles. Of each element in the compound, because what we're trying to do, remember, your subscripts in the chemical formula, they give you a mole to mole ratio. All right, and that's really, really important. So if the subscripts give you a mole to mole ratio, and we're given the mass of each of these components, then we would need to convert those masses into moles. All right, so we're given 6.87 grams of iron, which is Fe, and we're given 13.1 grams of chlorine, which is Cl. Now, going from grams, converting something from grams to moles is something we did in the previous sections. We're going to use the molar mass for each of those compounds, each of those elements. So use the molar mass and for the elements, and remember, we get those from the periodic table. Just look them up. and we can use that as our conversion factor. All right, so I have here 6.8 grams of iron. I'm going to use my molar mass for iron. Look it up on the table. It says for every 1 mole of Fe, I have 55.85 grams of iron. All right, that's the molar mass expressed in a conversion factor form. And again, I get this 55.85 from the periodic table. So the grams go away and I end up with moles of iron. I can then do the same thing with the chlorine. So I'm given my grams of chlorine. I look up the molar mass of chlorine on the periodic table. I see that 1 mole of Cl is 35.45 grams of Cl. The grams go away and I end up with moles of Cl as my unit. So if I plug those numbers in, I end up with our rudimentary mole to mole ratio for our elements in that compound. So what I can start doing now is start putting together a chemical formula. So remember, when you write the chemical formulas, you have, in this case, it's an ionic compound. You have a metal iron and a non-metal chlorine. So the iron goes first and the chlorine goes second. Let me do this in the same color. So Fe, and then I have Cl. And I can write those moles now as subscripts, right? So Fe is 0.123 and chlorine is 0.370. Now, when you write it this way, obviously that doesn't make a whole lot of sense because your subscripts cannot be decimals. They have to be whole numbers. So how do you convert these subscripts, which are just the number of moles, converted from the mass that we started with, how do we convert those to whole numbers? Well, we can do that by simply dividing by the smaller of the two. So we're going to divide both of them by the smaller number of the two. Right? So we're going to divide each of them by 0.123. Okay, so obviously now that's going to make this first one here, it's going to make that subscript 1. So we end up with Fe1. And then with the second one, with the chlorine, when I divide 0.370 by 0.123, all right, that's going to give me 3 as my subscript. So I end up with now my simplest whole number ratio, FeCl3. There's nothing simpler than that in terms of whole numbers for your subscripts. So this would be your empirical formula for this compound. All right, so to recap, what we do is we take the mass of each of the elements, we convert them to number of moles by using the molar mass. Once we get our number of moles, we can then start putting it together in our chemical formula. We write those number of moles as subscripts. And then we divide each of those subscripts by the smaller of the two. And then that is going to give us our empirical formula for our compound. All right, let's take a look at another example of how we can calculate the empirical formula. In our previous example, we were given the mass of each of the elements in grams. In some cases, you're not given the mass, but you're given the mass percent. And we can still use that to determine the empirical formula. So here we're told vitamin C, which is called ascorbic acid, has a mass percent composition of 40.9% carbon, 4.58% hydrogen, and 54.5% oxygen. And then we need to find the empirical formula for this compound. Now, we're not given the mass, but we're given the percent by mass. So if you're given that, so if given the percent by mass composition, okay, the easiest way to solve this, to get to the number of grams, would just be to assume that you have 100 grams of the compound. All right, so then the percentage by mass would simply be equal to that same number in terms of grams. So let's see what that means. So we have 40.9% carbon. Okay, so 40.9% carbon. So what is 40.9% of 100? Well, if you assume 100 grams, right, 40.9% of 100 would be 40.9 grams of carbon in that compound, right? That's why assuming you have 100 grams makes the calculation a lot simpler. You can assume any amount, but making it 100, assuming you have 100 grams, makes the conversion very straightforward. For hydrogen, we have 4.58%. So 4.58% hydrogen. That would mean then in 100 grams, we would have 4.58 grams of H. And then we have 54.5% oxygen. So in 100 grams, that would mean that we have 54.5 grams of O. So now, even though we weren't given the mass of the compounds, we were given the mass percent, we can just assume that we have 100 grams, and that way we've now determined the mass of each of those elements. The next step would be to convert these into moles, just like we did in the previous example. All right, so to get to moles, we would use the molar mass. So for carbon, the molar mass of carbon is 12.01, so 1 mole of C is 12.01 grams of carbon from our periodic table. Hydrogen, we look up the molar mass of hydrogen, 1 mole of H, 1.01 grams of H, and then for oxygen, we'll look that up as well. For every 1 mole of O, we have 16.00 grams of O. All right, so the same steps we did in the previous question. So if we evaluate all of those, we end up with 3.41 moles of carbon. We have 4.54 moles of H, and we have 3.41 moles of oxygen. So now we can take these and we can then start writing our formula for this compound, right? So we have our carbon, we have C, and this, we have 3.41 moles of it, so we put that as our subscript. We have 4.54 moles of H, so H 4.54, and then we have 3.41 moles of oxygen. All right, so again, that's our starting point, right? That's not the end by any means. What we're going to do next, because these are all decimals, we need to get rid of the decimals. We need to make them into whole numbers. We're going to divide each of them by the smallest number. So divide the subscripts by the smallest number, and that's 3.41. So we divide all of them by 3.41. So that would make this one here, we'd have 1 carbon. It would make the oxygen also equal to 1. And now the hydrogen, if we divide the 4.54 by the 3.41, we get 1.33. All right, so we've simplified it, but it's still not a whole number ratio. We have CH 1.33 and then 0. So when you're going to run into this in a couple instances where this here is not a whole number, or it's not even close. It's not like 0.999, or it's not 1.00001. When you have numbers like these where 0.33 is a third, or maybe if you had 0.25, which is a quarter, or maybe 0.5, which is a half, you need to get rid of that that fractional part of it, or that decimal part of it. And to get rid of it, what we're going to do now is to multiply all of them by 3. All right, so by multiplying everything by 3, let me rewrite this here. So we have C1, H 1.33, and then O1. We're going to multiply all of them by 3 because of this thing here. We need to get rid of that 0.33. So we multiply this by 3, we multiply the O by 3, we multiply the H by 3, so that's going to give us now 1 by 3 is 3, 1.33 times 3 is going to give us 4, and then our oxygen 1 times 3 is going to give us 3. All right, so this is going to be our simplest whole number ratio. This is going to be our empirical formula for ascorbic acid or vitamin C. So you may run into a situation where you get these decimal numbers when you do your first division. Your book has a nice little table that gives you what you want to multiply those by. All right, so we just went through the example where we ended up with a 0.33 in one of our subscripts, so we multiplied all of them by 3 to get rid of it. If you end up with any of the other ones, then those are the multipliers that you want to multiply them by to get rid of those fractions or those decimals. All right, so your empirical formula, the simplest whole number ratio of the elements in your compound.